What if every thought you had, every bit processed by a computer, and every learning algorithm running on an AI system had an energy cost, a physical footprint in the universe itself? Welcome to the Thermodynamics of Computation and Entropy in Information Theory, the science that unites energy, information, and intelligence. You're watching the Learning Studio, and in today's episode from our physics playlist, we'll explore how the same physical laws that govern heat and motion also shape how computers, and even minds, process information. You can watch the entire physics playlist by clicking the link in the description below. This topic is part of our section Physics of Information, Life, and Complex Systems, where we explore how the flow of energy and information builds complexity, fuels intelligence, and defines the boundaries of computation itself. When physics meets information, physics tells us that energy cannot be created or destroyed, only transformed. But in the 20th century, a revolutionary idea emerged: information itself behaves like a physical quantity. This realization was born from thermodynamics, the study of heat, work, and entropy, and it forever changed how we understand computation and learning. Every time a computer flips a bit, every time you erase or write data, energy is consumed and entropy increases. This means that even information, something abstract and mathematical, is grounded in physical reality. Physicist Rolf Landauer famously stated, "Information is physical." He proved that erasing one bit of information has a minimum energy cost, now known as Landauer's principle. It links computation directly to thermodynamic entropy, the measure of disorder or uncertainty in a system. In essence, thinking, learning, and computing are all thermodynamic processes. Entropy, the bridge between energy and information. Entropy in thermodynamics measures disorder. Entropy in information theory, introduced by Shannon, measures uncertainty. At first glance, these concepts seem separate: one belongs to physics, the other to communication theory. But they are deeply connected. Both describe the number of possible configurations a system can occupy. A hot gas, a shuffled deck of cards, or a scrambled digital signal, each represents a high entropy state. And when we reduce entropy, by organizing data, learning a pattern, or compressing a message, we spend energy to create order. This means every learning algorithm, every neural network, and every AI model obeys the same physical rules that govern steam engines and stars. The act of learning itself can be seen as a battle against entropy, the conversion of raw data, disorder, into knowledge, order. The thermodynamics of computation. As we build faster, smarter, and more powerful computers, the thermodynamic cost of computation becomes increasingly important. Each transistor switch and logic gate consumes energy and generates heat, a byproduct of entropy increase. In the quest for energy-efficient AI, scientists now study computation as a thermodynamic process. How much energy does it take to process information? Can we design algorithms that learn with less entropy production? This has led to new interdisciplinary fields like reversible computing, where information isn't destroyed and thus wastes no energy. Thermodynamic computing, which mimics the energy-efficient processes of nature. Neuromorphic systems, inspired by the human brain, a biological computer that performs billions of operations with just 20 watts of power. Nature has already solved the efficiency problem. The human brain, photosynthetic cells, and biological networks process information with minimal energy loss, far better than any machine we've built. By studying thermodynamics at the level of computation, we're not just building better hardware, we're rediscovering the physics of intelligence itself. AI, entropy, and the future of learning. In the age of artificial intelligence, entropy is the hidden currency of learning. Every deep learning model reduces informational entropy, transforming randomness into structured knowledge. And yet, that transformation always costs energy. Modern AI research now integrates thermodynamic ideas to design models that are both smarter and more sustainable. By understanding how energy, entropy, and information interact, we can create algorithms that learn more like nature, adaptively, efficiently, and self-organizingly. This merging of physics and information theory may lead us toward the ultimate goal, energy-efficient intelligence. A world where machines learn not just from data, but from the universe's most elegant rule, the conservation of energy and the optimization of entropy. Why it matters. The thermodynamics of computation reveals something profound. Every bit, every thought, every pattern we discover has a cost, a tiny ripple in the energy of the cosmos. Understanding that connection helps us build better technology, but it also deepens our view of reality. It tells us that computation, life, and even consciousness are not abstract, they are physical processes, governed by the same laws that shaped stars, atoms, and time itself. This is the Learning Studio, and this was our episode on thermodynamics of computation and entropy in information theory. If you enjoyed exploring how the universe turns energy into intelligence, make sure to subscribe, like, and check out our physics playlist linked below. In our next episode, we'll explore the physics of information and consciousness, where energy, entropy, and awareness merge into one of the deepest mysteries of existence. Because in physics, even the act of thinking obeys the laws of the universe.